Good day to you. This is David Pye of Pye Metallurgical International Consulting, located in the United Kingdom. And we're bringing today to you the heat treatment of aluminum alloys. And beginning with the nomenclature, temper designations, alloy elements, properties, and most importantly, the thermal processing. With this chapter, you, the student, will learn about the nomenclature of aluminum alloys, the temper designations of aluminum alloys, the alloying elements and the properties of aluminum alloys, the important properties of aluminum and its alloys, and the processing of the aluminum alloys by thermal means. Aluminum on its own has literally no usable strength, save that of being soft. It's very much like iron. Iron on its own exists in a soft condition and cannot become hard until we add small amounts of carbon. Then we can manipulate the strength of the iron by thermal methods. Pure aluminum cannot be strengthened by thermal processing in any way, shape or form. However, aluminum and its alloys can be mechanically manipulated and work hardened to some extent. Aluminum can be annealed if it has been work hardened. Therefore, we consider the addition of alloying elements to produce aluminum alloys of various mechanical properties. Some of the alloy elements that are added make it possible to be treated thermally to produce specific mechanical properties. The source of the aluminum is the ore which is named bauxite. Aluminum is 1/3 of the most prolific element in the Earth's crust, taking up approximately 8% after oxygen and silicon. The metal is non-magnetic, it's soft, silvery and coloured. Shows the bauxite ore as it has been mined and discovered. It's ready now for processing. Shows the aluminum as it's been extracted from the ore. Now we have a pure ingot of pure aluminum. Shows the numeration and identification of the methods of noting aluminum alloys, ranging from 1XXX and its alloys, or 1XXX and pure aluminum, 2XXX, which is copper, and so on right through to 9XXX. Although there are many alloying elements that can be added to the basic aluminum, there are generally only 5 elements that we add. The alloying elements are added to the basic pure aluminum at the melting procedure. Shows the grouping of the aluminum with those 5 elements. In the top block we have pure aluminum, and then we can alloy it with magnesium, which is just below aluminum, or manganese, which is also just below aluminum, or copper or zinc, which is below magnesium, or silicon, which is below manganese. Once the appropriate alloy elements have been added, we can now begin to categorize the alloys into very specific categories. And the categories are listed as follows: age hardening group, the cast alloy group, and the work hardening group. This once again is an illustration of the aluminum alloys in a tree form. Below the aluminum alloy we have the age hardening group, the cast alloy group, and the work hardening group. So, from the categories and with the alloy element additions to the aluminum, we're now able to identify the different groups of aluminum. These alloy groups are shown in the next slide. The identification nomenclature is a very simple and easy method to follow. And we'll start with the non-heat treatable aluminum alloys. You'll see in the top left-hand corner the box that says the non-heat treatable aluminum alloys. Below that we have the 1000 series, which is nothing but pure aluminum. And to the right of that we have the 3XXX, which is aluminum plus manganese. Below that line we have 4XXX, which is pure aluminum alloyed with silicon, 5XXX alloyed with pure aluminum and magnesium, and then 8XXX, which is aluminum and other specific alloys. These alloys are added all to manipulate the properties of the aluminum. Has an illustration of the groups of aluminum alloys in their numeration, 1XXX right through to 9XXX. It also shows the principal alloying element. Principally, there are three groups of aluminum wrought alloys that can be successfully thermally strengthened by solutionized and artificial aging. And those groups are the 2XXX aluminum alloys that are heat treatable, the 6XXX aluminum alloys that are heat treatable, and the 7XXX aluminum alloys that are heat treatable. Is an application of aluminum where it's used in, for example, aircraft structures, on undercarriage components, structural components, and of course on the surface covering. Scene now shows a tree formation of the heat treatable aluminum alloys. The top one is heat treatable aluminum alloys. Below that, on the bottom line, is the 2XXX aluminum alloys, and that with copper is strengthened by heat treatment. The 6XXX next to it is aluminum plus silicon, manganese, and that too is thermally strengthened by heat treatment. The 7XXX on the right hand side is now pure aluminum plus zinc plus thermally strengthened by heat treatment. The non-heat treatable aluminum alloys that can only be strengthened by work hardening, such as operations like bending, forming, straightening, stretching, fabrication, drawing, extrusion. The only thermal treatment that can be given to the non-heat treatable aluminum alloys are those thermal treatments that will anneal or stress relieve. There are no other thermal strengthening treatments that can be applied to the non-heat treatable aluminum alloys. Now starts to become a little more descriptive. Starting with the non-heat treatable aluminum alloys, we have the 1XXX, which is 99% pure aluminum, plus a trace of iron, plus a trace of silicon, plus 0.12% maximum of copper. And that has a fairly low tensile strength of 90 MPa, and it's used principally for sheet metals. 3XXX alloys, manganese is the principal alloying element with pure aluminum. To such analyses or specifications as AA3003 to AA1100 plus 1.25% manganese. You will notice that the tensile strength now begins to increase slightly, 110 megapascals, and it's a general purpose alloy. Now we move to the 5XXX, which is again pure aluminium and up to 5% magnesium. Identified also as AA5052, which is pure aluminum plus 2.5% magnesium, 0.2% chromium, and you will notice the tensile strength now is increasing quite significantly to 193 megapascals. You'll find that used principally in bus, truck and marine sheet metals. Moving to the heat-treatable alloys, we now have 2 XXX, which is aluminum plus copper plus magnesium, sometimes identified as AA2024, and that is aluminum plus 4.5% copper plus 1.5% magnesium plus 0.6% manganese, and you will notice the tensile strength now really increases quite dramatically to 442 megapascals. This alloy is used principally in aircraft structures. 6 XXX, which is aluminum plus magnesium plus silicon, and that would embrace specifications such as 6061, and that is aluminum plus 1% magnesium plus 0.6% silicon plus 0.3% copper plus 0.2% chrome. The tensile strength now increases up to approximately 290 megapascals, and it's used for general purpose structures. The 7 XXX is aluminum plus zinc plus magnesium plus copper, and that's translated to specification 7075, and that is aluminum plus 5.6% zinc plus 2.5% magnesium, 1.6% copper and 0.25% chromium. The tensile strength now increases up to approximately 504 megapascals, and it's once again used for aircraft structures. Is an illustration of the periodic table which identifies the metallic groups. Aluminum alloying elements. Alloying elements, their purpose is given below, are the alloying elements that are used to alloy aluminum for different mechanical and metallurgical properties. The first one we consider is antimony. This is used in very small quantities to improve corrosion resistance. Beryllium. This will tend to reduce oxidation at elevated operating temperatures, both for solutionizing and the part operational temperature. Bismuth. This is added to assist in the free machining characteristics of aluminum alloys. Boron is added to the aluminum alloy as a grain refiner and to improve the electrical conductivity of the aluminum alloy. It's sometimes seen with titanium as an added alloy. Cadmium. Because of its low melting temperature in liquids, it is not used in significant amounts, generally up to say 0.3%. Chromium. This element has a large effect on the resistivity of the aluminum alloy and is a common element that is added in amounts that do not exceed 0.35. If the chromium content does exceed 0.35, it'll tend to form very coarse constituents within the aluminum alloy. It reacts readily with iron, manganese and titanium. It further tends to assist with slag formation if the material is being cast. Copper. This element is generally found in the 2 XXX up to approximately 4.5%. It's in the heat-treatable aluminum alloys. The content controls of the copper being added as an alloying element is a maximum of 4 to 6%, generally around 4.5 to 5%. The reaction does of course depend on the influence of other alloying elements in the aluminum alloy. The strengthening effect comes after solutionized heat treatment, followed by precipitation or artificial age hardening. Copper, magnesium. Magnesium will add tensile strength to the aluminum alloy following the solutionized procedure. When the solutionized procedure has been completed, the real strength will begin to develop during the age hardening of the alloy, but with some sacrifice to the tensile strength. Iron can frequently be seen in aluminum alloys and has a high solubility level in the molten aluminum, as opposed to when the aluminum is in the solid condition, when it will have a very low solubility of approximately 0.05%. The iron can be seen microscopically as an intermetallic phase. The presence of iron will further reduce the grain size of the alloy. Lead. Lead is usually found as a trace element in commercial grade aluminum alloys such as the 1XXX up to 0.5%. Magnesium. This element is a major alloying element using up to approximately 17.4%, but generally controlled up to an approximate level of approximately 5.5%. Manganese. This alloy element is sometimes considered an impurity in aluminum alloys. It does not have any effect on the corrosion resistance of that particular aluminum alloy. It's further used to increase the strength of the aluminum alloy and to control the grain size structure. Molybdenum. Molybdenum is usually found at very low levels in the aluminum alloy at 0.3% and is used principally as a grain refiner. Nickel. The nickel content in most aluminum alloys should not exceed 0.04%. Above that amount, it will not go into solution and will usually combine with iron. There are alloys that will contain up to 2% nickel to increase the strength, but with a significant reduced ductility. Phosphorus. This element is considered to be a minor impurity and is usually found in the 1XXX series of the aluminum alloys. That is the pure aluminum series. Silicon. This element stands next to the element of iron as the highest impurity level in electrolytic commercial aluminum grades. It's found sometimes in the 6XXX series. It's also found in the castable aluminum alloys to assist with fluidity. If small amounts of magnesium are added to the silicon aluminum alloy, the alloy can be strengthened by thermal solutionizing and precipitation treatments. Sulfur. Sulfur is also present in aluminum with additions up to 0.2%. It's usually found in the 1XXX aluminum alloy series. Tin. Tin is an alloying element that is added to aluminum with concentrations up to 25% within the aluminum cast alloy specifications. The wrought alloy produced will generally contain approximately 0.05, and it will assist the speed of response at artificial aging after solutionizing of aluminum copper alloys. Tin will also aid the machinability of the aluminum alloy and is used in the aluminum copper alloys and the aluminum copper silicon alloys, and finally for the aluminum zinc casting alloys. Titanium. This element is usually found with very small amounts of up to 100 parts per million. Generally, it will reduce the electrical conductivity of aluminum alloys. However, it can be used in conjunction with boron. It is primarily used as a grain refiner for castings and ingots. Care should be exercised if welding has taken place, because welding is often conducted with filler rods of high titanium content. It will refine the weld structure and will assist in the reduction of the risk of weld cracking. But great care must be exercised by preheating and controlling the cooling rate to achieve the appropriate microstructure and necessary properties. Zinc. The addition of zinc in the commercial grade alloys does not improve the mechanical properties. It will help reduce the risk of stress corrosion cracking, and zinc will assist in improving the strength in the as-cast condition and an improvement in the tensile strength. Zinc will work best with other alloying elements for other mechanical property improvements. Zirconium. This alloy is added from approximately 0.1% up to 0.3% to form fine intermetallic particles within the matrix of the metal, to increase recrystallization temperature and to control the grain structure in the wrought aluminum alloys. We'll now demonstrate the principal aluminum alloys in relation to the nomenclature and identification. There are many alloying elements and combinations of alloying elements that can be added to the aluminum to improve tensile strength, impact strength, stress corrosion cracking reduction, recrystallization temperature, solutionizing temperature, and precipitation or artificial age hardening. We'll give you an illustration of the alloy numbers in relation to the treatment given in relation to the yield stress, UTS, and percentage of failure. Not all the possible alloying elements have been listed here. The content is just simply too great to be covered in this presentation. So suffice it to say that the previous list of principal alloying elements will be sufficient for this presentation. Each alloying element or groups of alloying elements will affect the strengthening mechanisms, the mechanical and metallurgical strengths and weaknesses. Temper hardness values. This section is going to discuss the identification of the temper hardness. Now, the designations are generally shown as follows. If you see the prefix of F, it simply means fabricated products. And this applies to aluminum products which are shaped by casting, hot work, or cold work. O prefix is for annealed products. This applies to wrought products that require annealing to obtain the lowest strength temper. The designation is also applied to cast products that have been annealed to improve both mechanical properties and dimensional stability. The H series is strain hardened on wrought products only. This means that the aluminum alloy has been strengthened by strain hardening and has or has not had additional heat treatment to produce a reduction in strength. After the H designation, it is usually followed by 2 or more digits. W prefix, which is water solution heat treated. This prefix is given to alloys whose mechanical strength changes naturally at room temperature over an extended time period. Heat treatable alloys. This system is based on the aluminum alloys of both cast and wrought alloys, which are heat treatable and employ the prefix of T or W. T1. T1 means cooled from an elevated temperature after shaping and naturally aged to an almost stable condition. T2 is cooled from an elevated temperature shaping process, followed by cold working and naturally aged to an almost stable condition. T3 is solution treated, cold worked and naturally aged to an almost stable condition. T4 is solution treated, cold worked and naturally aged to an almost stable condition. T5 is cooled from an elevated temperature shaping process and artificially aged. T6 now means solution treated and artificially aged. That is solution treatment and precipitation treatment. T7 means solution treated and overaged or stabilized. T8 means solution treated, followed by cold work and then artificially aged. T9 means solution treated and artificially aged, followed by cold working. T10 means cooled from an elevated temperature shaping operation, followed by cold working and artificially aging. Additional T variations can embrace the following. If you see TX51, that is plate, rolled or cold finished rod or bar. TX520 is extruded rod, bar and shapes. This is showing the groupings of the aluminum alloys, starting with pure aluminum in the top block of the tree formation. On the left-hand side, you'll see the non-heat treatable aluminum alloys. Below that, you'll see each block with the numerations. And those are 1XXX, which is pure aluminum. 3XXX, which is aluminum alloyed with manganese. 4XXX is aluminum alloyed with silicon. 5XXX is aluminum alloyed with magnesium. 8XXX is aluminum alloyed with other alloying elements, and 9XXX is a group awaiting usage. On the right-hand side of the tree, you'll see the three groups for the heat-treatable aluminum alloys. 2XXX alloyed with copper, 6XXX manganese and sodium, alloyed with the aluminum, and 7XXX aluminum alloyed with zinc. An illustration that shows you some of the photomicrographs that can be accomplished. Below the photomicrograph, you'll see small sketches, and those small sketches are our effort to try and bring a closer and further understanding of what is actually happening. TX52 applies to stress relief by compression products after solution treatment. TX54, this applies to forgings that have been stress relieved by restriking whilst in the die. T42 means solution treated from the O condition or F condition to demonstrate response to heat treatment, followed by natural aging to demonstrate its response. T62 is solution treated from the O or F condition to demonstrate response to heat treatment for artificial aging. Generally, what you will see is T1, that's cooled and naturally aged at room temperature. T4, solution treated and naturally aged at room temperature. T6, solution treated and artificially aged. T8, solution treated, cold worked and artificially aged. There are additional T variations shown as TX51 that applies to plate, rolled or cold finished rod and bar. TX510 is extruded rod, bar shapes and drawn tubing. TX511 are products that may receive minor straightening after tempering. Just an illustration, a tabular form of the T numbers for your information. Important properties of aluminum alloys. Magnetic properties. The magnetic property of aluminum and its various alloy and groups can also be affected by the alloying elements. In addition, there is always another influence that we don't always consider, and that is, at room temperature, the aluminum is oxidizing very slowly to form aluminum oxide. For operations such as extrusion or any hot forming operation, the aluminum surface will oxidize at a faster rate because of the process temperature and probable friction. Continuing the important properties of aluminum alloys, if iron is present in the alloy, it will combine with aluminum to form iron aluminum. As the compound forms and as the process temperature increases, so does the reactivity of the alloy of iron and aluminum, as well as its magnetic permeability. This must not be forgotten. It is also considered to be paramagnetic. Other alloying elements will also begin to change the magnetic permeability of that particular aluminum alloy. The formation of surface aluminum oxide will also begin to erode the wear and surface of, for example, shot sleeves for aluminum die casting, the bearing surface of an aluminum extrusion die. Aluminum oxide is extremely abrasive to both aluminum and to steel. Shows you a typical die casting system where the molten aluminum is being poured into the shot sleeve and then pushed into the die cavity. At this point in time, aluminum oxide is forming at its highest. Shows another die casting type operation with the liquid aluminum on the right hand side in a holding position, and the molten aluminum is being drawn off and pushed into the die cavity. Once again, massive aluminum oxide forming, which is abrasive and can abrade the shot sleeve. Is just a generalization of what will happen to aluminum as it is heated. Aluminum will always oxidize at its surface when in contact with water, oxygen-bearing gases, or heat. Aluminum oxide will always form on the surface of aluminum as the temperature is increased. And please note that aluminum oxide is extremely abrasive. It's showing what is happening to the aluminum at the surface when there is heat applied or it's in an oxidizing condition that the external surface is oxidizing. It shows you the aluminum oxide, which does provide a protective surface to further oxidation on the surface of the aluminum and protects the core. What then can be done to stop aluminum oxide from forming? Can we process the aluminum alloy under a nitrogen atmosphere? Please do not lose sight of the fact that aluminum is one of the strongest nitride formers. So nitrogen has the potential to form hard spots on the surface of the aluminum. Those spots will not be deep simply because of the residence time at temperature for solutionizing. There's really only two atmospheres that are non-reactive with the aluminum at any selected process temperature. And those industrial gases are argon and helium. They will not make any reaction whatsoever. But please do not consider the use of any oxygen-bearing gas. If aluminum alloy surface is to be protected from the formation of surface oxide, such as CO, CO2, nitrous oxide, steam will form oxide on the surface. We're now getting into the specific heat of aluminum. The specific heat of pure aluminum is a relatively high value when compared with metals like those of iron or steel. The specific heat is of great importance when calculating energy requirements to heat the aluminum workload up to the solutionizing temperature, and also for the precipitation temperature. It should be noted that the specific heat of aluminum will increase as the temperature goes from ambient temperature right up to the melt temperature. Illustrates the specific heat value of pure aluminum is averaged at 0.22. As I previously stated, that value will change from ambient temperature up to the melting point temperature. It's difficult to assign a constant value of specific heat, unless of course one is working at a specific heat solutionized temperature. In addition, and because we're discussing the aluminum heat treatable alloys, the alloying elements will also play a part in shifting the specific heat value at specific temperatures. The specific heat of aluminum will increase linearly from ambient temperature up to its melting point. The addition of alloying elements will then begin to affect the specific heat of that particular aluminum alloy. As I stated previously, we're generally going to work on a specific heat value of approximately 0.21. It is an illustration or a calculation of how we calculate the energy requirement necessary to raise the load up to its operational temperature. And it starts off with energy equals specific heat. That is the specific heat value of 0.21 plus the gross load. When you're assessing the gross load, do not forget that you need to take into consideration the furniture that the load is sitting on. And then we go into multiply that by the selected temperature. After we've got that value, we divide that with 3412 BTUs, and the 3412 value is the number of BTUs present in 1 kilowatt hour. The forging of aluminum alloys. The alloy content of the aluminum alloy grades will assist in the aluminum forging operations. As the alloy content of the aluminum alloy begins to increase, so does the degree of difficulty in forging that particular aluminum alloy. It is because the aluminum alloy content in that particular alloy will necessitate a greater forge press pressure. Because of the alloying element, the degree of potential for crack propagation will further increase. Once again, it will be necessary to have accurate temperature control on the furnace to ensure that no radiant forging temperature will cause eutectoid grain boundary melting, and also that the forge furnace temperature is uniform. That is very important. In addition to this, the time at temperature is also critical in terms of potential for grain growth. It will also be necessary to have a very clean forging furnace. This means cleaning out the process chamber on a very frequent basis. Shows what is happening to the billet as forging is occurring. There is a displacement of the metal, and if the metal is being displaced, then the grain structure is also being manipulated, as seen in the difference between the top illustration and the bottom illustration. Machining aluminum alloys. Machining, if the aluminum alloy is of the 1XXX, that's pure aluminum at 99% purity, the machining practice in either turning or milling will give you an experience of a gummy surface condition when machining. In other words, it's not machining very cleanly. The chips will tend to stick to the cutting tool surface. The alloying of the aluminum alloy will improve the machinability considerably. This is because the alloy now has a degree of hardness. Therefore, the machinability is greatly improved. If the solutionizing has not been done correctly, that is, quenching too low from the solutionizing furnace or quenching too slowly from the solutionizing furnace, then the non-solute elements will and do act as chip breakers. However, out of solution elements such as manganese, chromium and silicon will also act as chip breakers, but the tool life will decrease proportionately. Thank you sincerely for being present with me during this presentation. This now concludes the presentation, and I hope that you found it interesting and informative. The next step for you is now to take the self-assessment test. If you have any questions, please do not hesitate to contact me on either email or on the discussion forum. Thank you sincerely, David.